Assalamu alaikum warahmatullahi wabarakatuh and welcome to our podcast. My name is Ahmad Zhafran bin Mohamad Azmi and I have here with me two beautiful ladies. On my left, would you like to introduce yourself?
So thank you, I'm Raidah Qistina Binti Solehan. I'm a researcher from UTP.
And we have you on my right, would you like to introduce yourself?
I'm Shahirah Binti Azlan. I'm a process engineer from Nestle company.
So we have a professor and an engineer to assist me in understanding what enzyme immobilization is about, and I'm very eager to learn. Okay, so first of all, in order for us to understand enzyme immobilization, I hope you both agree, is that we need to get through the definitions. What are enzymes? What is immobilization? So enzymes, what are enzymes? Enzymes are macromolecular biological catalysts. So what do you mean by macromolecular? Basically big molecules like amino acids, proteins and things like that. So what are catalysts? Catalysts serves as a function to reduce the activation energy of a process so that it can enhance the process and you can actually speed up the process. So enzymes serve the same purpose as catalysts. Now, what is enzyme immobilization? So immobilization, in terms figuratively, you can imagine it as being the imprisonment of a cell or an enzyme through a medium or through a carrier or a support or a matrix, or even without any of that at all. So there are a few methods to actually immobilize enzymes. So one of which is adsorption, covalent bonding, entrapment, and cross-linking. So I'm not particularly clear about those methods. Could you actually explain to me how adsorption and covalent bonding actually works?
Okay, for the first process, which is adsorption process, so the adsorption process, it allows the enzyme to adsorb to the carrier or the support. There are a few types of carrier or support, which is mineral, organic, and also ion exchange resin. There are attachment between the enzyme and also the attachment between the support is due to three types, which is ion interaction, hydrogen bonds, and also van der Waals forces. There are a few examples of the adsorption process, which for the first is static process. For the static process, the enzyme and also the support will not have any stirring process because it will disturb the agitation. The agitation that happens will disturb the bonding between the van der Waals forces and also the enzyme. And second one is dynamic batch process. Dynamic batch process is a process where the interaction between the enzyme and also the support will have a hydrogen bonding. So this hydrogen bonding is developed because of the stirring and agitation that happens between the enzyme and also the support. The difference between the dynamic batch process and also reactor loading process is, for dynamic batch process, it only happens at one time. It's called batch process. And also for the reactor loading process, it is a continuous process. And for the lastly is electrode position process. Electrode position process is where the carrier is placed near to the electrode with the induced current, and also the ionic interaction between the enzyme and also the magnetic field is pull the enzyme towards closer to the carrier. And the second one is a covalent bond process. So for the covalent bonding process, the enzyme and the carriers have open compounds that aren't completely bonded. The carrier and enzyme will allow to react with each other by sharing the electrons to establish the covalent bonding. There are a few types of the enzyme that do this covalent bonding, such as carboxyls, amino, and hydroxyl. Meanwhile, there are a few carrier that will be used based on the enzyme that will be used is carbohydrates, synthetic agents, and also proteins. There are two examples that I can give for the covalent bonds, which is peptide bond that use amino and carboxyl group and enzyme, and the second one is deisolation, which use amino group and also the tyrosine enzyme. So that is from me, from adsorption and covalent bonding process.
So, thank you, first of all. So based on what I've heard is that adsorption and covalent bondings, they actually have a similarity of using supports
Yes.
with enzymes. But the only difference is the type of attractiveness that they have towards each other. Basically, one is non-covalent and the other is covalent.
Yeah.
Okay, so let's talk a little bit about what entrapment and cross-linking is. Could you explain?
Okay, so from my part, so entrapment is, you must know that the enzyme is actually has inside the porous matrix. So the porous matrix size will be depending on the enzyme size. So a matrix absorbs the enzyme, where at the same time it will prevent other molecules from also entering, such as the substrates and also the product of the reactions. So the enzymes then bond with the inner of the matrix, either through covalent or non-covalent bonds. So type of matrix for entrapment are such as gels, agar, and gelatins. So for another methods, the cross-linking. So it also known as the copolymerization process. So it is the subunits joins together to form a long chains or strains. So in this process, the enzymes are joined together via polyfunctional reagents. So the agents are cross-linked between each other and forming a net-like structure. So this process relies on altering the chemical composition of the enzyme to absorb, to actually enable the linkage. So this may result in the catalytic properties due to denaturing. So this process is different from other process because it does not rely on a support or carrier or the matrix.
Okay, that's quite interesting actually. It really does not rely on any kind of support. So it just relies on their own connections. Okay. So let's go a little bit into the technology and industry. I've heard that they use enzymes in, like, let's say wastewater treatment, and where they treat what do they call it, acetone trial, something like that, acetone trial waste containing wastewater. You see, when they use enzymes in that process, if it's left for too long, that process will actually produce something called hydrogen cyanide. So hydrogen cyanide is very, very poisonous, toxic, and it can lead to death. So the reason that they use immobilization of enzymes is to actually remove the enzymes and stop the process from going on for too long. The same goes with the food industry. Let's say for starch hydrolysis, they remove the amylase from the starch hydrolysis process, so that it actually prevents the starch from becoming too gelatinous. So these are very conventional, very typical, that we can see the applications of technology in the industry. Are there any examples of the uses of enzymes in the industry that are not too conventional, that are quite different?
So as I know about the non-conventional is the using of immobilized enzyme in a biosensor. So as you know, biosensor is a device, any device which is electrical device, mechanical or chemical device that used to detect biological species. So the usual ideal biosensor is when it responds to low concentration of analytes, and also ability to differentiate among the biological species according to the organization molecules. And the properties of the biosensor, it is extremely specific, highly sensitive, and also a low cost. That's why it is always used nowadays, because it's a low cost. And the advantages of this biosensor in a biological components is where its importance due to inability of loss of enzymes, and the stability will be maintained. The shelf life of biosensor also will become high, and it offers disposable to the products that use in stationery. And usually this biosensor function is to indicate of heavy metals, organophosphorus, chlorine, and pesticides that work on principle of enzyme inhibition. Besides that, biosensor also usually apply in immobilized glucose oxidase by electropolymerization, and this immobilized glucose oxidase will be indication of heavy metals. Besides that, there are also indication of mercury by immobilize the urease. The urease will be entrapped between PVC and cellulose layers on surface of iridium oxides electrons. Besides that, in cosmetic industry also, we also use immobilized enzyme. So as you know, in cosmetic industry, there are many types such as fragrance, hair and skin products, cosmetic, makeups. Besides that, each of these cosmetic product, they have different function, and also their lifespan is short actually. That's why we need to overcome it by using immobilized enzyme. Such as usually they will use lipase as enzyme that will be used in the cosmetic product, because lipase is enzyme that have ability to hydrolyze carboxylic compounds and having ester bonds in hydrophobic compounds. It also active ingredients in its formation acts as biocatalyst. Besides that, this lipase is essential for skin care, reflecting agent, and also thickeners and skin conditioners. So the advantages of using the lipase is because it is a non-toxic product because it didn't use any petroleum organic compounds, and also it reduced byproduct formation, and also economically and eco-friendly. Besides, lipase also will be used because it is a mild loosening to remove dirt in our skin, and also lipase also have an active compound that can be used in a perfume production, so it will be last longer. So that's all.
Okay, it's quite interesting. Cosmetics. I would have never thought that you would actually put enzymes on your face, but apparently so. Yeah. Okay, that's something new to me. So let's say we've been talking a lot about the present, and we've been talking a little bit about the past. So let's look into the future. So in pursuit of the objectives and the purpose of enzyme immobilization, how do you see enzymes being improved in the future, would you say?
Okay, so the current method that we have been discussed just now is actually good methods that we will use now. However, remember that whatever method that we choose, we actually want to enhance the enzyme stability and also the activity, so and become the most efficient one. So the selection of mode of immobilization is very important because we want to prevent the loss of enzyme activity by not changing the chemical nature of the enzyme itself. So a proper immobilization technique, we actually do more than just to make it a reusable enzyme. So it may be also used to improve the enzyme performance by improving some enzyme limitations. So the current methods that we discussed just now, it has their own pros and cons. So however, we want to improve for the future. So based on the research that I've read a lot, so I find that the nanotechnology technique is good potential for the future. So it basically uses nanoparticles as the enzyme, as the immobilization supports. In nanoparticles, it has the ability to adapt or to be adapted to many different functions or activities. Hence, the versatility will increase. And then, so on the other hand, studies show that nanotechnology technique it can reduce the protein unfolding and can improve the stability and performance of the enzymes. So what makes me think that nanotechnology method has a big potential in the future is because of its small size, and when it's small size, it has a large surface area. It has also high mechanical strength, mass transfer resistance. It has minimal diffusion problems, and it is very good in effective in enzyme loading. So present study shows that different types of nanomaterials are already available for enzyme embolization, such as carbon nanotubes, nanoparticles, magnetic nanoparticles, mesoporous media, nanofibers, and also the nanocomposites. So this shows that different enzyme can already use for the nanoparticles, because we have already nanomaterials different that suits for each enzymes. So,
that's a lot to take in. But that's all very interesting though. I think the most interesting point for me is the versatility, because enzymes, they react with very specific substrates and very specific chemical groups. So the versatility is, for me, is very interesting. So I guess that's all from us. That's all we have today. I would just like to say thank you to our associate professor, is it?
Yeah, see you again.
Professor Raidah, and our engineer here, Shahirah. I would like to say thank you very much for being here with me and giving me all this information so that I can take in and use in the future, inshallah. So with that, I would like to say thank you so much for you guys for also listening to us.
Thank you for watching. Thank you.
And that will be it. Thank you.